This video is about eigenvalues and eigenvectors of a square matrix. We have two objectives. First, we're going to define and compute eigenvalues and eigenspaces of a square matrix. Then we will prove some theorems about eigenvalues and eigenvectors. We'll start by considering the concept of direction and variance. If I have a vector x in Cn, and lambda is a complex number, if we look at this equation, a times x equals lambda x, what it implies is that if I multiply x by the matrix A, that is equal to x times a scalar. In other words, the direction of x is not changed, it's just the length that is changed. We could see what that looks like down here in a little diagram. This is a picture of C2. In general, we're considering Cn, but it's harder to picture higher dimensions, so for simplicity, we'll look at C2. We've got the x1 axis, the x2 axis. I've represented the vector x by an arrow, as we often do in C2. Normally, if I multiply x by a matrix A, I'd get something like this. The length would be changed, in this case it's shortened, and the direction would change, in this case rotated by some angle theta. However, if x is invariant under multiplication by a, its direction invariant in particular, then ax would look something like this. The length would still be changed. In this case, I drew it longer. It could be shorter like this or longer. But the direction is not changed. It's still pointing in the same direction. It turns out that this is a very special relationship between vectors and matrices and these scalars. And whenever this equation is satisfied, we give these things special names. In particular, we'll say if A is an n by n matrix, and there is a non-trivial solution of this equation, ax equals lambda x that we were just looking at, then we call lambda an eigenvalue of A, and x is an eigenvector associated with lambda. Notice that an eigenvector can never be zero by definition. That's because non-trivial means that x cannot be zero. Notice if I plug in a 0 for x here and here, the equation is satisfied. That's called the trivial solution, but we're not interested in that one. So the trivial solution to this equation is not an eigenvector, only non-trivial solutions. So it's important to remember that an eigenvector can never be zero. Eigenvalues can be zero. There's no restriction on what lambda can be here. And if we plug in a 0 for lambda here, we get 0 on the right side, but the left side may or may not be satisfied. So a times x would have to be equal to 0 for 0 to be an eigenvalue of a. Another important thing to keep in mind is that only square matrices have eigenvalues and eigenvectors. So for this entire chapter, we're only going to be considering square matrices. Okay, as we consider how would we find eigenvalues and eigenvectors, let's look at the defining equation again. If I want to solve this equation, I have to be careful. I can't use the algebra of real numbers like we may be tempted to. For example, I may want to divide both sides by x, cancel the x's, and then say a equals lambda. Would that work? Well, first off, a dead giveaway should be that A is a matrix and lambda is a number. So this doesn't even mean anything. A matrix cannot be equal to a number unless this is a 1 by 1 matrix. But in general, this is n by n. Another problem is this is not defined. There's no such thing as division for vectors. If you remember, in a vector space, we define addition, how to add two vectors together, and how to multiply a vector by a scalar. Division is never defined, so we can't do this. Okay, well, what do we do instead? We can subtract lambda x from both sides, and then we can write lambda x as lambda times I times x. That might seem like a strange thing to do, but I is the n by n identity, and if I multiply I times x, I just get x. And the reason I do that is so that I can factor an x out on the left side, leaving a and lambda I. The reason I need a factor of I in here is because inside here, I've got a matrix minus something, and that's only defined if this something is also a matrix. So if I had a minus lambda, that wouldn't make any sense. Just like a cannot be equal to a scalar, a minus a scalar is not defined. But a minus the matrix, lambda I, is defined. So we just have to solve this equation for lambda and x. First, we're going to define the characteristic equation and the characteristic polynomial. Given an n by n matrix A, the characteristic polynomial of A, written like this, P for polynomial with a subscript a, so that tells us the name of the matrix, of x, is defined to be the determinant of a minus x times I. And then the characteristic equation of a is the characteristic polynomial, this up here, set equal to 0. And then to find the eigenvalues of A, we simply solve the characteristic equation. Okay, so let's do some examples to illustrate this. First, we'll start with a small little 2x2 matrix. Remember, we can only find eigenvalues and eigenvectors of square matrices. Before we continue, let's consider a general algorithm to find the eigenvalues and eigenvectors of a matrix. We're going to use this algorithm over and over again in this section and in the sections that follow. The first step, given a square matrix A, is solve the characteristic equation to get the eigenvalues. In general, we'll get a bunch of different eigenvalues in step 1. Then in step 2, for each eigenvalue, we solve this equation, a minus lambda I times x equals 0, and we'll see where this comes from as we go along, to get the eigenspace, which we'll define as we go as well, associated with each eigenvalue. Notice it says for each eigenvalue. So if I get 3 eigenvalues up here in step 1, I have to do step 2 3 times. We only have to do step 1 once, but in general, we'll have to do step 2 multiple times, once for every one of the eigenvalues that we get in step 1. Okay, so let's try that here. First, I solve the characteristic equation. Remember, p sub a of x is equal to the determinant of a minus xi, and I set that equal to 0. Well, how do I solve this, and what am I even solving for? Well, a is given to us. That's a matrix. I is the n by n identity, in this case 2 by 2, so that's also known. So the only thing we don't know is x. I skipped a step or two from here to here, so let me fill that in just to be really clear. Okay, so from here, we can go up and look at what is a minus xi. Here's a minus x times I, the 2 by 2 identity. Multiply the x into each of the entries in the identity matrix to get this matrix. And then subtract term by term, 1 minus x, 2 minus 0, 3 minus 0, and 2 minus x. And then I take the determinant of it, so I replace the square brackets here and here with the straight brackets here, and that's how I get from this step to this step. Once you've done this a few times, you can just skip these steps. If you look at what we did to go from a to the determinant of a minus x times I just take the determinant of a and I subtract an x from each of the main diagonal entries. So I'll have 1 minus x, 2 minus x, and then these two stay the same. And then we use the definition of the determinant to evaluate this determinant. Since this is a 2 by 2, I multiply across 1 minus x times 2 minus x, and then subtract 3 times 2, which is 6. And then notice what I have here. This is just a polynomial in x. So I multiply this out and combine like terms, and I get this polynomial. X squared minus 3x minus 4 is equal to 0. And we solve that equation the way we normally would in a basic algebra class. We can factor the polynomial as x plus 1 times x minus 4 equals 0. So x plus 1 is equal to 0, or x minus 4 is equal to 0, which means x equals negative 1 or x equals 4. These are the eigenvalues of A. So we can say the eigenvalues of A are minus 1 and 4. Then, for each of these 2 eigenvalues, we are going to do step 2 of the algorithm we just looked at. So we do step 2 twice, once for negative 1 and once for 4. Okay, so first for negative 1. It doesn't matter what order you do them in. I just arbitrarily decided to do negative 1 first. Now, I already said that we're going to solve this equation, a minus lambda ix equals 0, to find the eigenspace, which is the set of all the eigenvectors. But let's see where it comes from. We take our original equation again, ax equals lambda x. We do the same thing. We subtract lambda x from both sides, multiply x in this term by I, factor the x out, and we get this equation. But now I know lambda, so I'm just going to replace lambda with negative 1 here and simplify, and I have a plus I times x equals 0. Well, this is a matrix equation. And we know how to solve this equation. In fact, it's a homogeneous equation, which makes it even easier. So a plus I, again, I skipped that step, but we could write that out to make it really clear. So here's a plus I, add term by term. There's a plus I times x equals 0. And we solve this the standard way by row reducing the coefficient matrix. Here's our coefficient matrix. It row reduces like this. So we've got 1x1, plus 1x2 equals 0. So we solve this equation and we get x1 equals minus x2. We can write the parametric solution like this. X is equal to x1, x2. x1 is minus x2. x2 is free. Factor out the x2 and we can say x is tv, where v is this vector, minus 1, 1, and t is any complex number, except it can't be 0. Why can't it be 0? Because remember, x cannot be 0. Well, this vector is not 0, so we're okay there. But if t is allowed to be 0, then x could be 0, which we know is not an eigenvector. So t can be any complex number except for 0. The solution set here is almost the span of the set containing this vector. This set contains the 0 vector, though, and the solution set does not. We're going to give this set a special name, however. This set is going to be called the eigenspace for A, corresponding to the eigenvalue -1. And here's our definition of eigenspace. If A is a square matrix with an eigenvalue lambda, the set of eigenvectors associated with lambda together with the 0 vector. So we add the 0 vector to the set of eigenvectors. That's called the eigenspace of A. It's written with this cursive E with a subscript A and then lambda in parentheses. And this is read the eigenspace of A for lambda. And it's equal to the null space of A minus lambda I, which is what we just solved for previously. This is the null space of A plus I, or A minus -1 times I. And remember up here we had A minus lambda I. So in this case lambda is -1, and that just simplifies to A plus I, which is where we get this expression. All right. So that's what an eigenspace is. Now we're going to define a few more things before we come back to this example. If A is a square matrix with an eigenvalue lambda, the algebraic multiplicity of lambda, written alpha with a subscript A of lambda, is the multiplicity of the 0 lambda in the characteristic polynomial. If you remember from basic algebra, multiplicity of a 0 in a polynomial can be easily identified when we factor the polynomial. In the fully factored form of the characteristic polynomial, the algebraic multiplicity of lambda is the exponent of the x minus lambda factor. For example, down here, if this is our fully factored form of the characteristic polynomial, lambda 1 is one of the zeros, lambda 2 is another 0, up to lambda k. So there are k eigenvalues for this matrix A. X minus lambda 1 is raised to the m1 power, x minus lambda 2 is raised to the m2 power, etc. Well, if we look at, for example, this first term with lambda 1 in it, the algebraic multiplicity of lambda 1 is m1. It's the exponent of the x minus lambda 1 factor in the fully factored form of the polynomial. So that's what all this means. In general, it's pretty easy. Once you get your characteristic polynomial in fully factored form, you just look at the exponents to get the algebraic multiplicities. So the algebraic multiplicity of lambda I is just mi. The algebraic multiplicity of lambda 1 is m1. The algebraic multiplicity of lambda 2 is m2. For lambda k, it's mk, etc. Okay, one more definition before we come back to finish the example. If A is a square matrix with eigenvalue lambda, the geometric multiplicity of lambda, written gamma with a subscript A of lambda, is the dimension of the eigenspace of A for lambda. Okay, let's go back to our example. We found the eigenspace for lambda equals -1. In fact, we can come back here and write that down. So the span of the set containing this vector, which we found in the solution set to the equation A minus -1x equals 0, is the eigenspace of A for -1. Okay, so now we continue and we're going to find the eigenspace of A for 4. And we do the same thing. We solve the equation A minus lambda I times x equals 0. Well, we're now going to replace lambda with 4, and we are just going to take the matrix A and subtract a 4 from the main diagonal. So A is 1, 3, 2, 2. To form A minus 4i, we leave the off-diagonal entries the same, and we subtract a 4 from the main diagonal entries. So we get this matrix, we row reduce it. Notice you're always going to get at least one row of zeros at the bottom because this matrix will be singular. And we know that because there's a non-trivial solution to the equation here. So if it's a 2 by 2 matrix, well, the second row is going to be all zeros and the first row will not be. We write down the equation corresponding to the first row. We solve for x1 in terms of the free variable x2. We write the corresponding parametric solution. We can see x is tv, where v is 2, 3. t is any complex number except 0. Notice I got a fraction up here when I solved for x1 in terms of x2, but I can use any scalar multiple of this vector as a basis for my eigenspace. So I can multiply both entries by 3 to clear the fractions and get a 2 here and a 3 down here. T can be any number. So this vector is included in the eigenspace. This vector is included in the eigenspace. I can multiply this vector by any number I want, and that vector is in there. And I can use any of those vectors as my basis vector. So the set of all scalar multiples of this vector is the same as the set of all scalar multiples of this vector. So that's a little trick I like to do. When I get fractions in a basis vector like this, I just multiply it by the lowest common denominator of all the fractions to clear the fractions. So the eigenspace of A for 4 is the span of the set containing 2, 3. Okay, let's do another one, and we'll do this one quicker since this is our second time through. Here is a 3 by 3 matrix A. We solve the characteristic equation to find the eigenvalues. So the determinant of A minus xi, set that equal to 0. Remember, to form the matrix A minus xi, basically we're just going to take the matrix A, subtract an x from each of the main diagonal entries, and leave the lower triangle and upper triangle the same. So here's the main diagonal entries with x subtracted from them. The lower triangle and the upper triangle are the same. I skipped the steps of doing the determinant. Notice there aren't any zeros in this matrix, just coincidentally. There just don't happen to be any zeros in here. If there were, we could take advantage of those zeros as we saw in the determinants video to simplify the computation of the determinant, but in this case there aren't any, so we just go through and use the definition of the determinant as we saw before to compute the determinant. So we have x cubed minus 12x minus 16. We factor that as we normally would in basic algebra, and we find that it factors into x minus 4 times x plus 2 times x plus 2. And so our eigenvalues are 4 and minus 2. Then we find the eigenspaces associated with each eigenvalue. I'll start with 4 first. I'm going to solve the equation a minus lambda I times x equals 0. I replace lambda with 4, form the matrix, simplify it, row reduce it, and then write down the corresponding equations. Notice I've got 2 non-zero rows here, so each row will give me an equation, here and here. And then I've got one free variable, x3, 2 dependent variables, x1 and x2. So x1 is 1/2 x3, x2 is also 1/2 x3, x3 is free. I can factor the x3 out, and I get x3 times a half, 1. We'll do our trick that we did before, multiply this by 2 to get 1, 1, 2 to clear the fractions. So the eigenspace of A for 4 is the span of the set containing 1, 1, 2. We repeat that for lambda equals minus 2. Notice I skipped even more steps here, which is great once you get the hang of this. All I really need to do is write down the matrix that I'm going to row reduce, which is A minus lambda I. Well, lambda is minus 2, so A minus a negative 2i is A plus 2i. I form that matrix by adding 2 to each of the main diagonals of A to get these numbers. Row reduce it, write down the corresponding equation. In this case, I only get one equation in 2 rows of all zeros. So I've got 2 free variables, x2 and x3. So x1 is x2 minus x3. x2 and x3 are free. I can rewrite this vector as x2 times this one plus x3 times this one, and now I've got 2 basis vectors for my eigenspace. In other words, the solution set can be written as x equals su plus tv, where u is this vector and v is this vector, and s and t are any complex numbers, of course, except for 0. Now, strictly speaking, we would want to say that they can't both be 0 at the same time. If s is 0, and this is gone, but t is not, well, then x is not 0. Likewise, if t is 0, but s is not, then x is not 0. So if we were more careful here, we would say s and t are not both equal to 0 at the same time. Okay, then the eigenspace associated with the eigenvalue minus 2 is the span of the set containing these 2 vectors. Okay, one more example. We have another little 2 by 2 matrix, which may seem like we're going backwards or going back to easier examples, but as you'll see, we're going to get complex eigenvalues here, so it's a little bit harder. We do the same thing. We solve the characteristic equation. We subtract an x from each of the main diagonal entries, do the determinant, get our characteristic polynomial. This, if you try to factor it, you won't be able to. So you can use the quadratic formula to find that x is 2 plus or minus the square root of 2 times I. So we've got two complex eigenvalues, 2 plus root 2i and 2 minus root 2i. So we'll start with 2 plus root 2i. We do the same thing. We're going to replace lambda with 2 plus root 2i. So we do that here and here, and then we can simplify like this. And now at this point, we would want to row reduce this matrix. And Wolfram Alpha or other computer algebra systems may be able to do that. If you're using a TI-83 or 84 or some other handheld calculator, you may not be able to do that. The TI-83 and 84 can't do it. But we can take advantage of what we know about this matrix to avoid having to row reduce at all. Remember, this is a singular matrix, and when I row reduce it, the second row is going to be all zeros. What that means is both of these equations tell us the same relationship between x1 and x2. So I can pick either one and just write down the corresponding equation. For example, if I pick the second row here, I can write it as 1 times x1 plus this number times x2 equals 0. Then I solve the equation for x1 in terms of x2, simplified here. Then I can write the parametric solution. X1 is equal to this expression. So x1 is 1 plus root 2i times x2. x2 is free. Factor out the x2. And then I've got this vector in C2, which is a basis vector for the eigenspace of A for 2 plus root 2i. So here is the span of the set containing the vector. That's the eigenspace. For 2 minus root 2i, the steps are very, very similar. So we subtract 2 minus root 2i from each of the diagonal entries of A, and instead of row reducing it, pick one of the rows to solve for x1 in terms of x2, and then write down the parametric solution. Here's our basis vector. And the eigenspace of A for 2 minus root 2i is the span of the set containing this vector. All right, now we're going to look at some theorems that simplify some of the computations that we've done, as well as some of the problems that we'll do in future sections. All right, let A be a triangular matrix. Remember, that's upper or lower triangular. So here's an example of a lower triangular matrix where the upper triangle is all zeros. The diagonal entries can be anything. The lower triangle can be anything. The eigenvalues of a triangular matrix A are just the diagonal entries. So here they are. That's a direct result of a theorem that we saw in the determinants chapter that says that the determinant of a triangular matrix is just the product of the diagonal entries. Well, if I subtract the lambda I from each of the diagonal entries to form A minus lambda I, the determinant of that matrix is just the product of those diagonal entries. And there is our characteristic polynomial in fully factored form already, which is really nice. So we can see lambda 1 is d1, lambda 2 is d2, etc., up to lambda n, which is going to be dn. We don't even have to compute eigenvalues if I have a triangular matrix, upper or lower. The eigenvalues are simply the diagonal entries of the matrix. Okay, the next theorem says if I have some eigenvectors, v1, v2, up to vp, corresponding to distinct eigenvalues, and that's an important word there, distinct, meaning none of these eigenvalues are equal to each other, then the set of these vectors is linearly independent. That's a really curious conclusion. Eigenvectors corresponding to distinct eigenvalues are linearly independent. That's how we can say that succinctly. The proof is a little bit long, so I'm not going to go through the whole thing. It's a proof by contradiction, and I don't know if we've done one of those yet in the class, so I'll just outline the form of it. In general, to do a proof by contradiction, what you do is assume that the thing that you're trying to prove is not true, and then you reason to a contradiction and conclude that your assumption was wrong and the thing you're trying to prove is true. So we're trying to prove that this set is linearly independent. So we're going to start by assuming that it's not linearly independent. In other words, we're going to assume that it's linearly dependent. Then we will reason to a contradiction. So read this and see the reasoning and see where the contradiction comes from. Once we get down here, we get to the equation v sub m plus 1 is equal to 0, and v is an eigenvector. But we know that eigenvectors can't be 0. So that's a contradiction of something that's already known to be true, namely eigenvectors can't be 0. But if the set is linearly dependent, then this eigenvector has to be 0. Well, that's a contradiction, so our assumption must be false. Therefore, the set must be linearly independent. All right, we're going to finish up this video with a couple of theorems about Hermitian matrices. These will be really handy later. First, we'll say if A is a Hermitian matrix and lambda is an eigenvalue of A, then lambda is a real number. Remember, in general, lambda is a complex number. but Hermitian matrices have real eigenvalues. That's basically what this theorem says. If A is a Hermitian matrix, all of its eigenvalues are real. And the proof is just a direct application of the properties of Hermitian matrices. In particular, the inner product of V with AV is equal to the inner product of AV with V. Remember, normally, if I want to move the A from here over to here, I'd have to take the adjoint of it. So we could add an extra step here just for clarity. The inner product of V with AV is equal to the inner product of A star V with V. A star is the adjoint, the conjugate transpose. And Hermitian matrices have the property that they are equal to their own adjoint. So Hermitian means A star equals A, or A adjoint equals A. We can replace the adjoint of A here with just A. Well, then I can say AV is equal to lambda V. Why? Because V is an eigenvector associated with lambda, as we saw here in the beginning of our proof. Okay, well, if I factor the lambda out using the properties of inner products, the lambda comes out and then it gets conjugated. I can factor the lambda out here. If it comes out of the right-hand side of the inner product, it does not get conjugated. But if it comes out of the left-hand side of the inner product, it does get conjugated. So we end up with this equation, lambda times the inner product of V with V is equal to the conjugate of lambda times the inner product of V with V. Well, the inner product of V with V here and here is equal, so that means lambda has to be equal to its conjugate. Well, any complex number that's equal to its own conjugate must be real. So Hermitian matrices have real eigenvalues. We can use that theorem to prove the next one. If A is Hermitian, then any two eigenvectors from different eigenspaces are orthogonal. Remember, that means that their inner product is 0. We'll start with this expression, and it may not be obvious at all why we would do this, but let's say V1 and V2 are eigenvectors of the Hermitian matrix A associated with eigenvalues lambda 1 and lambda 2 respectively, where lambda 1 is not equal to lambda 2. How do I know that lambda 1 is not equal to lambda 2? Well, up here, from different eigenspaces, that's what that means. So different eigenspaces means corresponding to different non-equal eigenvalues. So I'm going to look at this expression, lambda 1 times the inner product of V1 with V2, and I'm going to bring the lambda inside here using the properties of inner products, and so it gets conjugated because it's coming in on the left. If I brought it in onto the V2, it would not be conjugated, but bringing it in on the V1 means I have to conjugate it. And now I'm going to use the fact that lambda 1 is a real number. How do I know that? Well, by theorem 5.1 that said that the eigenvalues of a Hermitian matrix are real. So the conjugate of lambda 1 is simply lambda 1. And then I'm going to replace lambda 1 V1 with a V1 because V1 is an eigenvector associated with lambda 1. Therefore, it satisfies the equation a V1 equals lambda 1 V1. Then I'm going to move the A over onto the V2, again using properties of Hermitian matrices in inner products. And then I'll replace a V2 with lambda 2 V2, bring the lambda 2 out, and I get lambda 1 times the inner product of V1 with V2 is equal to lambda 2 times the inner product of V1 with V2, which we see here. If I subtract lambda 2 times the inner product of V1 with V2 from both sides, I can factor out this inner product, and I've got the quantity lambda 1 minus lambda 2 times the inner product equals 0. That means either lambda 1 minus lambda 2 is 0, or the inner product is 0. Well, if lambda 1 minus lambda 2 is 0, that means lambda 1 equals lambda 2. But we know that's not true. Remember, lambda 1 and lambda 2 are distinct, so this can't be true. That means the inner product has to be 0. And what does that mean? That means V1 is orthogonal to V2, which proves the theorem. Lastly, before we finish up this video, I want to go back and look at the examples that we did and label the algebraic and geometric multiplicities of each of the eigenvalues. So in our first example, we had this 2x2 matrix. Here was our characteristic equation, and this was the factored form of the characteristic polynomial. If we think of the x plus 1 term having an exponent of 1 and x minus 4 term also having an exponent of 1, the algebraic multiplicity of -1 is 1. The algebraic multiplicity of 4 is also 1. Then when we found the eigenspace of A for -1, we can see that there's one vector in the basis. The set inside here is the basis for the eigenspace. That means the dimension of this eigenspace is 1, and that is the geometric multiplicity. So we can say the geometric multiplicity of A for -1 is 1. Likewise, since the eigenspace of A for 4 is one-dimensional, there's one vector in the basis, the geometric multiplicity, this is gamma sub A of 4, is equal to 1. In the second example, we had the 3 by 3 matrix A. When we factored the characteristic polynomial, we could have written the x plus 2 times x plus 2 as the quantity x plus 2 squared, like this. And if we did that, then we can see the algebraic multiplicity of 4 is 1, and the algebraic multiplicity of -2 is 2. When we found the eigenspace of A for 4, we got the span of the set. We can see that there's a single vector in this basis, so the dimension of this eigenspace is 1. And that's the geometric multiplicity of 4. And then we can see here's the eigenspace for -2. It's got two vectors in the basis, so the geometric multiplicity of -2 is 2. Finally, our last example, we got two eigenvalues that are complex, and we didn't factor. I said we couldn't factor this. What I really meant was we can't factor it over the reals. Of course, it does factor over the complex numbers, and if we write it in factored form, we can see the algebraic multiplicities. So here's the factored form of the characteristic polynomial, x minus this complex number raised to the 1 power times x minus this complex number raised to the 1 power. So we can see the algebraic multiplicity of 2 plus root 2i is equal to 1, as is the algebraic multiplicity of 2 minus root 2i. From the eigenspace of A for 2 plus root 2i, we can see there's a single vector in the basis, therefore the geometric multiplicity is 1. And similarly, this eigenspace has dimension 1, and so the geometric multiplicity of 2 minus root 2i is also equal to 1. All right, that finishes our video on eigenvalues and eigenvectors. We defined and computed eigenvalues and eigenspaces, which is really the main point in this video. It's the main thing you need to be able to do given a square matrix. Find all of the eigenvalues and the corresponding eigenspaces, and then determine the algebraic and geometric multiplicities for those eigenvalues. And then we prove some theorems that sometimes make those computations easier and will also be useful in future chapters.